is about to start. Please come back to the session. Okay, so hello everyone. Thanks for coming to the afternoon session. This session is about network verification. We have 4 very interesting talks in this session. They cover topics like P4 verification and how to make control plane verification scale to large networks, plus another talk about how to build high performance on FVs. So the first speaker today is Dave Walker. So he is a professor at Princeton. So we will hear how he talk about control plane compression.
Thank you. So it would be wonderful if Ryan Beckett were here today to give this talk. He's really the leader of this project. He just graduated with his PhD from Princeton, and he is making his way to Seattle right now to start a job at Microsoft Research soon. I'm the substitute for Ryan. So if you look at the news, you'll find that a lot of it is bad, and it's not just politics. Sometimes our networks malfunction, and a lot of the reason for that is misconfiguration of various routing devices. One of the jobs of our community is to develop new verification techniques to try and mitigate this problem. And there is some good news on the horizon in that for the last decade or so, people have been developing new tools to try and make our networks more reliable. The first wave of network verification tools focused on data plane verification. That's not the topic of this talk, though. I'm going to be talking about tools that will help accelerate the performance of control plane verification tools. And this includes both simulation tools like Batfish, as well as various control plane verification tools like Bagpipe, Arc, Era, or Minesweeper. These tools seek to, in general, verify a variety of properties of all of the data planes that are produced by a control plane, ensuring that these data planes have properties such as reachability, that they prevent using the network as transit by peers. They may test for equivalence of routers or subnets. They might detect loops or ensure the absence of black holes. In most of the cases, these tools scale highly nonlinearly. So for example, the Minesweeper tool operates by reduction to SAT and SMT, and this NP-complete problem scales exponentially in the worst case. So while Minesweeper works really well if your network has on the order of a couple of hundred of devices, depending on the properties you're trying to verify in the policy, once you start looking at networks beyond that scale, the performance simply falls off a cliff and verification becomes impossible. And of course, industrial data centers are operating at scales much larger than this and will continue to grow in size. So the central contribution of the current paper is an algorithm that will take a large network control plane and analyze it rapidly and produce a much smaller network control plane that is behaviorally similar. Once you have this smaller network control plane, you can take any other or many other verification tools, such as the Minesweeper tool or the Batfish tool, or if you have your own network verification tool, you could run Bonsai, our compression tool first, generate a small network, and apply your tool to the smaller network. Because the verification time curve is exponential, even a linear compression can give you exponential improvements in performance. So we've analyzed our tool empirically and shown that it can reduce network sizes by a factor of 5 to 7 in the number of nodes, and a factor of 7 to 10, or 7 to 100 even, in the number of edges. We've also done some theoretical analysis, and we've proven the correctness of our algorithms as well. Okay, so how does it work? So in order to explain that, I need to tell you a little bit about our network model. To simplify, first, we're going to consider a situation in which we only have one destination to route to. And the formal model, which I won't describe in this talk, but is described in the paper, is based on much past work on the stable paths problem and on routing algebras that have been developed in this community earlier. So we're routing towards a single destination. What this destination does is it disseminates a number of route announcements to its neighbors. Those neighbors will select announcements that they receive and then further propagate the announcements. At a certain point, each node has chosen an announcement, and we call such choice a solution to the routing problem. We also call it a labeling of the nodes with route announcements. Visually, I'll depict such solutions using orange arrows. So these orange arrows are in the opposite direction that the route announcements were disseminated, and they represent the flow of traffic through the network. Okay, so our goal is to take one of these large routing systems and to compute a smaller routing system. And what we'd like is that smaller routing system to have similar solutions to the larger one. The main difficulty is that we can't just compute the routing solutions of the large network because that's, in a sense, what verification is trying to do. And so if our compression algorithm were to just compute the solutions, it wouldn't have any effect on speeding up the overall process. So what we really need is a quick test that suffices to guarantee similarity of the solutions between the small and the big network. Okay, so, but before I get to that, how are these small and big networks related? Well, we typically call the small network an abstraction of the big network, and such abstractions are defined by a pair of functions. The first function, f, tells you how to map nodes in the concrete network into abstract nodes in the abstract network. And the second function, h, tells you how to map route announcements that would travel through the concrete network into route announcements that travel through the abstract network. So for example, in this latter case, route announcements are often defined by paths through a series of nodes. So in the concrete network, that would be a path of concrete nodes, such as the path A, B2, D. In the abstract network, we don't have the concrete node B2, so we need to define that path as A, B, D. So this function h maps between those two different kinds of paths. Okay, so I mentioned that we need some kind of quick test that will guarantee the similarity of concrete and abstract networks. So one component of that condition is what we call the for all exists requirement. So intuitively, it says that concrete nodes have to have similar connections topologically as the abstract nodes. So more specifically, so in this case, the idea is that because there is a connection between abstract nodes B and A, there must be a connection between all of the related green nodes and some red node. So for example here, B2 must have a connection to some red node, either A1 or A2, and indeed it does. It has a connection to A2. But if we were to go ahead and add a node, such as the node C1, and try to color it green, placing it into the same group as B1 and B2, this would be an invalid abstraction. The picture on the right would be an invalid abstraction of this green network, of this concrete network, because C1 needs to have an edge to some red node, and it doesn't. Don't worry, though, we can generate a valid abstraction of this network. We just need to refine the current abstraction, making it a little bit bigger. And the way we might do that is to add another node, blue node C. And now our abstraction does satisfy the topological condition. So the second condition that we need is a condition we call transfer equivalence. And that basically says that concrete route announcements are processed in the same way as abstract route announcements. So to give you a picture of how that works, suppose we have a concrete route announcement, and it is passed from the node B2 to A2. And in the course of doing that, it gets transformed by a route map, for instance, into the concrete announcement C2. If we go ahead and abstract C2, we might get some abstract announcement A2. Okay? Well, this transformation needs to be the same as if we were to abstract the announcement C1 first and then process the abstract announcement A1 in the abstract network. Another way to say this is when dealing with verification and abstraction, one often sees these box-like commuting diagrams, and so this is a common kind of condition that we need in order for the abstraction to be valid. Okay, so if we have both of those two conditions, the for all exists requirements and the transfer equivalence requirements, then we have a guarantee that the abstraction will compute a globally similar solution as the related concrete network. And so what that means basically is that, for instance, if A2 computes a best route to the destination, then A will also compute a similar best route to the destination. Those will be similar modulo the abstraction function H. Okay, a corollary of this theorem is that our abstractions preserve a whole bunch of really important properties for network operators. So they preserve reachability, routing loops, hop count, property called multipath consistency, and properties like waypointing. Okay, so I've told you the conditions a valid abstraction must satisfy, but I also need to tell you how to find an abstraction. So what's the algorithm? To set things up, the first thing we do when running the algorithm is we take the configurations and we transform all of the processing into BDDs, binary decision diagrams. The reason we do this is because once we've translated all the functions into BDDs, we have a very quick test to be able to determine when two transformation functions are equal. And so this allows us to have a constant time test for this transfer equivalence property that we need to check for. Okay, so once we've done this setup phase, the algorithm is really very simple. We start by dividing the network into two abstract nodes, and then we check to see if our conditions, transfer equivalence, and the topological for all exists condition holds. If it doesn't hold, then we repeatedly divide the abstraction into smaller and smaller pieces until we find an abstraction for which our conditions are satisfied. In the worst case, we might just wind up back with a concrete network, but in practice, this doesn't happen. So here's our little example again. So we start out by having the destination in its own abstract node, and all of the other nodes are in a separate abstract node. So if we look at this network, we can see that the nodes B1 and B2 are connected to an orange node, but the nodes A1 and A2 are not connected to an orange node. So what that means is that the for all exists condition fails, and we need to subdivide this big abstraction into two smaller ones, where B1 and B2 are in a different partition from A1 and A2. So if we do that, we get the following abstraction that now has three abstract nodes. But again, we can see that the condition fails. Now it's the case that B1 is connected to a node A1 in the blue partition, but C1, which is also in the green partition, is not connected to any blue node. So once again, the for all exists condition fails, and we need to again subdivide the green partition. Okay, so once we do that, now we have four partitions. And if you go and check all the nodes and all the partitions, you'll find they all have the same connections. And so we satisfy the requirements, and we've now discovered a correct abstraction of the original concrete network. So once we have that, we can just return this collection of nodes and their connections, and a tool like Minesweeper could go ahead and analyze that abstract network, decide whether or not it had the desired reachability properties. Okay, so as an aside, BGP is behaving badly, and my friend Jen Rexford tells me that this happens quite commonly. So the problem is that you might think that if two BGP nodes have syntactically identical configurations, that they process all message announcements that they receive the same way. But that's not true because BGP loop detection discards routes differently in one node than another. And so the problem with this is the condition that we're looking for, which is transfer equivalence, winds up never holding in the presence of BGP. So I can't go through the details here, but if you look in the paper, you can find a theorem that we prove about the behavior of BGP that limits the number of behaviors it can have, and a new algorithm that will accommodate BGP in this kind of setting. Okay, so we've evaluated our tool on both some synthetic benchmarks and on some real networks. And I wanted to first show you, in some sense, what the best possible case scenario for our tool is. So in this scenario, we are trying to verify a fat tree topology that has a very simple policy. It just does shortest paths routing. So on the vertical axis, you have the time it takes to do verification, and on the horizontal axis, you have the size of the network that we're trying to verify. And the blue line represents the Minesweeper tool on its own, and the orange line represents the Minesweeper tool when we've applied Bonsai, which does compression first. So the blue line has the familiar exponential curve that I showed you at the beginning of the talk, and the orange line is practically flat. And the reason for this is that the synthetic network is incredibly symmetric, and in just one or two iterations, Bonsai always identifies the same abstraction, which is very, very small. And so the cost of both compression and verification together is roughly just the cost of compression, which in this very special case winds up being essentially linear in the size of the network. And the cost of verification just winds up being a constant overhead because the size of the abstraction never grows. But most networks have less symmetry in this. For example, just to take another example, a ring network, Bonsai plus Minesweeper is still better than Minesweeper alone, but you can see an increasing curve. So when we applied Bonsai and Minesweeper, or Bonsai and the BATFIS simulation tool to some real case studies, we got some exciting results. So in a data center, which has about 600,000 lines of configuration and about 197 devices, we were able to compress the network into approximately 26 nodes. So compression took only about 15 seconds for each destination. There are 1,269 destinations, which each have to be done separately, but those can all be done in parallel. So this compresses nodes on an average of by about 6 times and edges by about 100 times. We also looked at this in the context of a wide area network, which again had about 600,000 lines of configuration and about 1,000 devices. It compressed the network into about 137 different roles. The compression took about 2 seconds, and the compression ratio was about 5 times in terms of the number of nodes and 7 times in terms of the number of edges. One note I wanted to make is that we still have work to do in that even after compression, Minesweeper was unable to scale in order to process this wide area network because of the particular combination of protocols that were used that Minesweeper is not very good at dealing with. However, BATFIS, the simulation tool, was able to analyze this wide area network, and it wasn't able to analyze the 1,000 node network. So we're making verification possible in situations, or simulation possible in situations where it wasn't before. Okay, so Bonsai has a number of limitations. So in particular, our algorithm is a greedy algorithm, and it's not guaranteed to find the optimal abstraction. In addition, we have made a variety of very specific choices about the kinds of techniques we've used to abstract messages. There are other choices that we could make that might lead to better results. And so continued research here, I think, will be very interesting. The biggest limitation of Minesweeper is that while it will preserve the existence of paths, it doesn't preserve the number of paths or the number of neighbors. Indeed, it's trying to reduce the number of paths and reduce the number of neighbors in order to reduce the amount of time it takes to verify those networks. But as a result, it doesn't preserve fault tolerance properties. And so that's an interesting direction for future research as well. The last point is that we haven't studied the problem of whether or not bonsai preserves divergence. And that might be something that we could look into as well. Okay, so to summarize, a bonsai is a tool that's complementary to most of the other research in control plane verification. It's complementary because it takes a concrete control plane and produces a much smaller control plane that you can then go ahead and use one of your other verification tools off the shelf on that smaller control plane. So it preserves many path properties, but it does not preserve fault tolerance. We've done a theoretical analysis with respect to a generic algorithm and proven a number of its properties. Thank you.
So, is there any questions?
Hi, Nate Foster, Cornell. Really cool work. I was curious about the limitations slide I appreciated, and it seems like there's maybe even a little more there, because if your abstraction is, if your topological abstraction is making many nodes equivalent, but your property distinguishes finer than that, then it seems like the reasoning you do on the abstract network wouldn't be preserved, or rather, reasoning you would do on the concrete network is not preserved when you do it on the abstract network.
Yes.
So waypointing, for example, seems like it could be complicated. If you have a non-waypoint node and a waypoint node that get merged, then the reasoning you do on the abstract network wouldn't tell you necessarily if the concrete network will have those waypoints.
Yes, I'd agree with that. So if there's any node that is particularly named in your property, you wouldn't be able to collapse that together with some other node. So right now, the destination is always concrete. If there's any particular node that you're interested in, you could also keep that node concrete, and the rest of the algorithm would work fine, allowing you to compress anything that wasn't that node.
I see. So you'd probably take the sort of working set of your property and then fix those, and then do the abstraction refinement having fixed those.
Yeah.
If I can ask one other follow-on question, it seems like loops would also be tricky. So there must be something that prevents you from taking a loop in the concrete network and abstracting it into a single node that doesn't have a loop?
Yeah.
Maybe only self-loops?
Right, so you're not allowed to have self-loops in the abstraction or in the concrete network.
I see, cool. Thanks.
Hi, this is Xing from Alibaba. Great work. I do have a question about the definition of symmetric in your talk.
The definition of symmetry?
Yes.
Okay.
For example, so in BGP there are, the BGP is quite complex. There are quite a few properties, like number of prefixes, the neighbor policies. So in your definition, to what extent does it mean those two nodes are symmetric, I can merge them?
So, I mean, the property that we're looking for, in some sense, is that two nodes are similar when they process routing announcements in the same way. So, incoming routing announcements are transformed in the same way, and they are produced, and they produce output routing announcements that are the same. So that's the key property that we're looking for.
I see. So then a following up question is, you were talking about Badfish does work, but for Minesweeper it doesn't work. So
because of the scaling properties
I
of
know,
the two systems.
but I understand for Minesweeper, we actually don't care the prefix. We actually encode the prefix into some like a variable formula. But for Badfish, we actually do the actual prefix, right? We do the actual simulation in Badfish. So in that case, so for example, in this particular topology, different rack are announcing different prefixes. Do you actually merge them into the same node?
Yeah. So what we do actually for both Minesweeper and for Badfish is so the destination is always treated separately.
Mm-hmm.
So we actually, for every different destination location, we redo the compression. So that's on the evaluation slide. I skimmed over this very quickly, but the data center, for instance, there were 1,200 something destination classes. So basically, we did the compression and the verification separately 1,200 different times.
I see.
But all of that work can be parallelized. So every destination is independent. So really, the goal is to get verification for each destination to be as quick as possible.
I see. Thank you.
I really enjoyed your talk, Aditya Akela from Wisconsin. I was wondering, going back to your slide where you talked about how many roles you discovered in your tool discovered in the networks that you analyzed. It made me wonder if your algorithm is basically mining templates in configurations. I understand BGP is subtle, so forget that. But are you basically just identifying router templates?
Yeah, that would be one way of putting it. Although the templates that we're identifying are very simple, and you could potentially do much better. I mean, this would be future research that we haven't considered, but I can imagine doing better if the kinds of templates that you have are more general. So actually, let me give you an example of, so in one network that we analyzed, that network, for every router, it was generating a different community to say, I'm router X. And when that network did that, basically we couldn't get any compression because really every single router was doing something slightly different. But nobody ever used those I'm router X tags. And so we changed the way our abstraction worked, and we basically elided that community.
Right. No, I was talking about the common case. It seems like for most networks, there will be some general templates. And so if you just identify templates and compress on the basis of that, you may get much far along the way in terms of the compression benefits you're getting. And the rest of the things may be because of these subtleties that you're pointing out.
Yeah, so when you say templates, what I'm thinking of is bits of code that have parameters in them.
Yeah, exactly.
And so an interesting thing, though, is to figure out how to generate those parameters. So I would say at the moment, if you want, yes, that's what our tool is doing. It's just identifying all of the nodes that are the same, but then it's taking these topological conditions into account. Because just because two nodes process route announcements the same way, if they're in a different topological position in the network, you can't necessarily combine them together. So you need a combination of topological conditions and semantic conditions on the processing functions. But those two things together are essentially all this tool is doing, and it's doing it quickly using some smart data structures such as BDDs. And but yeah, that's the essence of what's going on.
Great, thanks.
Okay, let's thank the speaker. We're running out of time, so we're running late. Please take a question offline. Okay. So our next speaker is Jie Liu. Right now, he's a research engineer in Barefoot Networks, and he graduated with a PhD from Cornell, where he works on distributed system and compiler. And today his talk is about verifying P4.
All right, thanks for bearing with me. Thanks for the introduction. So I'm here to talk about P4V. This work was done at Barefoot in collaboration with Bill Hallahan from Yale, Robert Soule from Vigado, Nick McKeown from Stanford, and Nate Foster from Cornell. So fixed function routers. How do we know that they work? Well, we test them, and there's a whole industry that builds appliances for exactly this purpose. But testing is expensive, and routers usually support lots of packet formats and lots of protocols. The good news is that we only need to pay this cost once during manufacturing, and all users of the device benefit. Okay, so let's look at programmable routers. How do they work? Well, chips in these devices expose a programming interface. For example, these switches have a Tofino chip, which can be programmed with the P4 language. These devices are the new hotness. They enable rapid innovation with novel uses of the network, such as in-band network telemetry and in-network caching. The downside, though, is that we no longer have this nice economy of scale for traditional testing. So what do we do? Why not verify? The nice thing about P4 is that we get a nice, precise, bit-level description of the data plane behavior. So let's give programmers language-based tools to verify their programs. As a side benefit, we also get to verify fixed function devices because P4 happens to also be used for hardware description language, as a hardware description language. P4V is an automated tool for verifying P4 programs. It considers all paths while also being practical to use on large programs. It includes basic safety properties that are useful for any program, and it's an extensible framework. With it, you can verify custom program-specific properties, or you can do assert-style debugging. Before we go into P4V, let's take a quick look at P4 itself. P4 programs have header declarations. They have parsers that convert bit streams into headers, actions that modify headers and specify forwarding behavior, and they have tables that apply actions based on header data. And finally, they have controls, which, for our purposes, we can think of as sequences of tables. P4 programs are written against an abstract hardware model called PISA. In this model, packets are parsed into headers, and a sequence of tables is applied in the ingress pipeline before the packet is queued. After queuing, another sequence of tables is applied in the egress pipeline before the packet is finally deparsed onto the wire. Parsers, tables, and controls in the language map naturally onto this abstraction. Oh, and I should say that the deparser is automatically derived from the parser, and we'll come back to this point later. Now, P4 is a low-level language, and like any low-level language, there are lots of gotchas that you need to consider when writing a program. So let's explore some of these by example. So imagine we were writing an IPv6 router with an access control list, or an ACL. First, in the ingress control, we apply the ACL table. The table reads the IPv6 destination address, and depending on the address, we either allow or deny the packet. We allow the packet by setting the egress port, and we deny the packet by dropping it. Simple, right? What could possibly go wrong? Well, the first problem is if we didn't receive an IPv6 packet, then the IPv6 header will be invalid. When this happens, the table will read arbitrary values, so the intended access control policy might be violated. Even worse, we might end up reading values from a previous packet, and this can be a serious side channel vulnerability. Real programs are complicated enough that it's hard to keep the validity of all the headers in your head. So one property that we'd want to verify is header validity. A second problem is that the ACL table might not have a rule that matches the destination address. In this case, the forwarding decision is unspecified, and what happens to the packet is completely up to the hardware. Even if it does what you expect, the code isn't very portable. So we also want to verify that the packet has unambiguous forwarding. Okay, so let's kick it up a notch and add 6-in-4 tunneling. Let's add a tunnel decap table to decapsulate the inner IPv4 header and promote it to a layer 3 header. We keep the IPv4 header around so that we can continue to refer to its fields for, say, access control. Later on, we terminate the tunnel by removing the IPv4 header and setting the either type to IPv6. Looks great, right? Well, let's scrutinize this intermediate form for a quick second. It turns out that there are a couple of issues here. To understand why, we need to look behind the curtain a little bit. In PISA, state is copied verbatim from ingress to egress. But in reality, some architectures use the parser and deparser to bridge headers from the ingress pipeline to the egress pipeline. So what if we are on an architecture that does this? Well, remember how I said that the deparser is derived from the parser? So because IPv4 and IPv6 are mutually exclusive protocols, their headers can be deparsed in any order. Suppose the IPv6 header is deparsed before the IPv4 header. Then when we reparse the packet, because the either type still says IPv4, the IPv6 header will be reinterpreted as an IPv4 header, and we get garbage. So a third property that we want to verify is reparsability. Let's take another look behind the curtain. Hardware devices have limited resources, so compilers have options to improve resource usage. For example, if headers are mutually exclusive in the parser, then the compiler might assume that they stay mutually exclusive for the rest of the program. This is important to get large programs to fit under hardware constraints. For instance, mutually exclusive headers might share the same registers. So in our example, IPv4 and IPv6 are mutually exclusive protocols, so their headers might share the same registers. So when we decapsulate the IPv6 header, we might end up clobbering data in the IPv4 header. Parsers are complicated in practice, so it's hard to keep track of which headers are mutually exclusive. So another property that we'd want to verify is the mutual exclusion of headers. There are many other properties that we might care about. We can classify them into 3 categories. There are general safety properties, such as header validity. There are architectural properties, such as reparsability and mutual exclusion of headers. There are also program-specific properties, which you can write as custom assertions in the P4 program. For example, you might assert that the IPv4 TTL is correctly decremented on every packet. Now let's look at some of the challenges that we face when building when building P4V. The first challenge is that the P4 language spec doesn't give precise semantics. So what we did was we defined semantics by translation to GCL. This is a simple imperative language that goes back to Dijkstra. How do we know that our semantics were reasonable? Well, we tested them. We built a symbolic executor for GCL to generate input-output tests for several programs. We compiled the programs with Barefoot's compiler and ran them on the Tofino simulator. For each test, we checked whether the actual output from the simulator matched the expected output from the symbolic executor. In this way, we gained confidence that our semantics closely matched a reasonable implementation. A second challenge we faced was that a P4 program is really just half a program. The rules in the tables are not statically known. They are populated by the control plane at runtime. So our translation turns each table into an unconstrained, non-deterministic choice. For example, the ACL table is turned into a choice between the allow action, the deny action, and a table miss. But real control planes are carefully programmed, so tables rarely take arbitrary actions. So to rule out false positives, we need to model the behavior of the control plane. We do this with control plane interfaces. These are given as a second input to P4V alongside the P4 program itself. Control plane interfaces contain annotations that constrain the choices made by tables. We write these annotations in a clean, domain-specific syntax. For example, this particular annotation says that a certain rule is inserted into a table. More generally, though, annotations can be abstract or symbolic. Here's an example of a rule that expresses coordination between two tables. One table decapsulates a tunnel header exactly when another table terminates that tunnel. A third challenge is reducing the annotation burden. Many verification tools require annotations for both assumptions and assertions, but P4V can automatically generate assertions for many properties, including header validity and reparsability. A fourth challenge is scaling to large programs. For this, we avoided compositional verification because of the high annotation burden. Symbolic execution is a popular technique that explicitly explores paths in the program, but P4 programs tend to be very branchy with all the parsers and tables that are typically in a program. So exponential path explosion is an issue for P4. So instead, what we did was we generated a single logical formula. This formula is valid exactly when the program satisfies its assertions on all execution paths. We then hand this single formula to a SAT solver, which tells us either that the verification passes, or it gives us a counterexample for a failed assertion. Oh, and we also do some standard compiler optimizations, like constant folding and dead code elimination. So here's a quick look at the P4V architecture. First, we start with a P4 program and a control plane interface. We take these and we translate to GCL, and we auto-generate assertions. Next, we perform some standard compiler optimizations and generate a logical formula. We hand this formula to Z3 in the back end, and we either get a pass or a fail. If verification fails, we output a counterexample containing an input packet, a program trace, and the violated assertion. To see what it's like to use P4V, we tried it out by verifying header validity in switch.p4. This is a large program that implements the functionality of a data center switch. We chose header validity because it's a cross-cutting property. It involves reasoning about almost all control paths in the program. So how feasible is it to write control plane interfaces? Well, what we found was that you can do it in a couple of days of effort. You can see the paper for details, but briefly, the annotations we wrote captured basic sanity and well-formedness conditions. Interestingly, we found some bugs. We found that the parser admitted ill-formatted packets. We found that some multi-table constraints seemed to be impossible to satisfy the control plane. And we found tables that read invalid headers. To evaluate the performance of P4V, we ran it on all the programs we could find. And we ended up with a diverse set of programs. Some of these were open source and some were proprietary. This plot shows the running time for checking header validity. The individual programs are lined up on the horizontal axis, and on the vertical axis, we have the running times in log scale. The light blue bars give verification times for just the programs without a control plane interface, and the dark blue bars give the times for verifying with a control plane interface. All but 3 programs were checked in less than a minute, and most programs were verified in well under a second. Our front end was able to handle all of the programs, but the Z3 backend ran out of memory on Hyper P4. This is a program that tries to virtualize the data plane. And as it turns out, we ended up generating a formula that was too big for Z3 to handle. P4V is part of a big project that the community has been working on since SIA in 2005. Momentum was gained with Anteater and header space about 6 years ago. And our new innovation here is a more detailed model of data plane functionality, and we engineered a tool that scales well. There's lots more to be done. Currently, we only support P4.14 and Tofino, so it'd be nice to support P4.16 as well as other architectures. There's also work to do in control plane interfaces. For instance, right now, we write them by hand. It'd be nice if we could synthesize them instead from program traces. And how about verifying network-wide properties? This is a problem that quickly becomes undecidable, and we might need new abstractions to be able to scale well. So to sum up, I've presented P4V, a tool for automated all-paths verification that scales to large programs managed by a separate control plane. Thank you.
Hi, question right here. Really, really cool work. So if you go to the evaluation, I was really puzzled by that graph. Yeah, so here you're showing basically that adding the control plane interface doesn't make verification faster, and that's kind of puzzling because basically you're constraining what you can have in the table. So you think that Z3 has to answer, well, simpler queries in a sense, right? So why is this?
Well, that's a good question. I think I don't really know for sure, but my guess would be that well, I don't really know what the inner workings of Z3 are, so it's hard for me to answer. But my guess is that the control plane annotations don't really make these formulas any smaller. If anything, they make them bigger because we're adding more constraints into the system. So we have to have more formulas to handle that.
And just another quick question. Are these control plane interfaces related to the property you're trying to specify, or you write them once and you can verify multiple properties to them?
So what we did was we wrote control plane interfaces specifically for the property that we were trying to verify. But I think in a real setting, what really should be done is that these control plane interfaces should be developed alongside the P4 program itself, because the P4 programmer knows exactly what these control plane interfaces should have in them. So in particular, like the programmer knows all the details that the control plane should have in them. Yep.
Thanks. Hi, Arseniy Dasranik, EPFL. This is a really exciting project, and I hope it's gonna develop. In particular, I wonder how do you handle the dynamic state in the switch, like registers, for example, that may change from packet to packet?
So good question. So when we translate to GCL, basically the initial state of those registers are havocked. We assume that they have a random value. They can have any arbitrary value. But as soon as they are written to, we fix that value.
So you over-approximate them?
Yes. Yes.
Thank you.
Nikolai Bjorner, Microsoft Research. What logic do you need for the verification? Meaning, what features are used to express your verification conditions? Is it purely bit vector reasoning, or do you use functions?
It's all bit vector, yeah. So we basically just use the bit vector package of Z3. Okay, thanks.
Okay, our next speaker is Grace Liu. She is right now a fifth-year PhD student at George Washington University. And right now she's doing an internship in Microsoft Research Cambridge. She will graduate this year, so feel free to talk to her if you can offer her a job opportunity.
Yes, thanks for the introduction. Hello, everyone. Let's switch to the NFV world, and welcome to the Macrobox presentation. This work was done with my colleagues Yuxing, McKeown from George Washington University, KK from UC Riverside, and my advisor, Tim Wood. In the recent years, the performance of NFV platforms has been significantly improved by leveraging kernel bypass I/O libraries, such as DBDK and NetMap. Some representative high-performance platforms are ClickOS, BAS, and NetVM. However, these platforms mainly focus on L2 and L3 processing that limits the types of NF that can support. In more detail, let's view them in the protocol layer model. These platforms can pass protocols up to the network layer and support NFs such as simple firewall and NAT. If you look at the design of these systems, they are based on a packet-centric model, where each NF in the chain is given every packet for processing. This design is intuitive since the protocol data unit at network layer is the packet. However, if we look at the application-level protocols, they actually care about data instead of individual packets, and they rely on the transport layer to deliver correct data. There are a large group of NFs operating at this layer, such as a load balancer and a web proxy. A current solution with packet model is incorporating a TCP stack, such as MOS, for each NF. As a result, a packet needs to go through stack processing multiple times, and the stacks are doing redundant work. To see how much cost we are paying for the redundant processing, we did an experiment. We set up a chain of NFs between a web server and a client, and the client requests 8 KB files, and we change the length of the chain as shown in the x-axis. And we compare the processing latency for 2 cases. For the forward case, each NF just forwards individual packet. And for the stack case, each NF performs bad stream reconstruction using MOS stack. From the figure, we can see, as the chain length increases, the latency for the NFs performed the reconstruction increased significantly compared to the simple forward case. This is redundant since the bad stream can be created only once. So a natural question to ask is, how can we remove the redundancy within a chain? Ideally, we can avoid the actual overhead by performing TCP processing only once, and then exposing the result to a sequence of NFs. And one possible solution we do not select is to combine the network functions and stack into a single monolithic process. This can make it easier to reuse the results of stack processing, but it can create problems for NF development, deployment, and management. Using a single process makes it difficult to reuse legacy applications, hurts fault tolerance, and prevents packaging NF along with all of its dependencies. Instead, our focus is on the NFV environments where NF must be deployed as isolated VMs or containers, since we think this better fit for today's development model, especially with the recent growth in microservice architectures. So our first idea is to consolidate stack processing within a chain and move the processing from NFs to the NFV framework. This allows NFs and stack to be implemented as isolated components, such as containers, while still eliminating redundant processing. However, this is not enough, as a monolithic stack with full functionality is not efficient. To see how different stack functionality affects the performance, we did another experiment to evaluate the throughput of several NFs. The first case is a layer 2 forward NF, which just forwards packets over the NIC and gets the highest throughput. We use this as a baseline. The second NF acts as a splicer and performs the TCP handshake with the client. After the connection is established, it hands the connection off to the application. This only requires a partial TCP stack to check the state transitions and do a sequence number rewriting. The third NF not only detects the start and end of the connection, but it also checks 4 TCP connection states. Finally, the fourth NF performs bad stream reconstruction in addition to state checking. From the results, we can see the throughput drops almost by half as we add more functionality into the stack. And since each NF may not need 4 TCP functionality, adding unnecessary stack processing could affect the performance. So how can we avoid unnecessary processing in the stack? When we have a chain like this, where different NFs require different levels of processing. Our second idea is to split the stack into modules based on functionality and customize processing for each NF or each chain. This lets them get different combinations of stack functionality without paying any extra cost. With this, we take one more step further, but it's still not perfect, since we only focus on the middle box NF so far. But there are other endpoint applications, such as web proxies, which need complete control over the bus stream. In current deployments, they use completely different underlying frameworks for protocol support, which is separate from middle box NFs. Ideally, we want to use a unified platform to manage them all. So the third question we ask is, how to transparently manage both middle boxes and endpoints? Our idea is to use a flexible event interface that can represent packet, data, and legacy events for a variety of services, and support many types of stacks ranging from simple L2 processing all the way up to the full endpoint processing. Based on these 3 ideas, consolidate stack processing, customizable stack modules, and event communication interface, we propose macro boxes. Okay, I've talked why we need to improve NFV frameworks and the 3 design ideas of macro boxes. In the rest of my talk, I will show you how we design macro stack and macro event in more detail, as well as evaluation results. Let's begin with macrostack. We divide TCP processing into 5 basic macrostacks so they can be composed together based on the needs of an NF. This macrostack is specialized to avoid redundant processing and can support a wide spectrum of NFs, from a simple IDS that just needs to monitor TCP state to a web proxy that needs a 4 TCP endpoint. And the first is the layer 203 macrostack, which does network layer processing to determine what flow it is associated with and maintain minimal state, such as flow status. Then is the TCP monitor method stack, which tracks the TCP state and reconstructs the bad stream of both the client and server side of a connection. The third one is the TCP Spicer macrostack, which can redirect the TCP connection after establishing a handshake without support for modifying the bad stream. Note that in some ways, the Spicer is actually simpler than the monitor macrostack because it can redirect connection with only sequence number rewriting and does not need to reconstruct the full bad stream. And to support endpoint applications, we have TCP endpoint macrostack, which contains the 4 TCP logic and can terminate and respond to client requests directly. Finally, we have TCP split proxy macrostack, which sets up 2 TCP connections with client and server respectively, and allows NF to perform bad stream transformations. This shows how our macrostacks build on top of each other. The split proxy macrostack is built using 2 endpoint macrostacks with an interface to an NF, such as a video transcoder. In between, that is able to transform the bad stream. Next, let's zoom in and see how to use one macrostack module to support a chain of NFs. This sounds simple, but it poses consistent challenges. Since stack and NFs may be running in the containers on different cores in parallel, and they all need to access the stack state. This means the stack state could be inconsistent. When NF raises state, well, the stack has changed it based on the new packet arrivals. For example, NF1 raises the connection state of the flow the green packet belongs to, but the stack has changed it when processing the red packet. This leads to stack inconsistency. To ensure correctness, we need to guarantee protocol stack state associated with each packet will be consistent when each NF processes this packet. A safe approach is processing packets of the same flow sequentially. So we hold the red and blue packets until the last NF of the chain finishes processing the green packet, which is NF3 in our example. This approach can achieve correctness since only one core is accessing the stack state. But if we put it into the timeline, we can see this leads to an inefficient layout. Since only one core is doing useful work, while others are idle. So how can we improve it? Our solution is to take a stack snapshot and associate it with the packet so that NFs can access the state in the snapshot while the stack is processing the new packets. From the timeline, we can see each core continues to process packet 1, 2, 3 without waiting, and the core utilization has been largely improved. The tricky thing about snapshot is it's easy to copy some data such as connection state. However, copy the bad stream for each packet is not feasible. Fortunately, bad stream can be treated as a append-only data structure. Thus, we only need to store a pointer to the end of the bad stream at the time of receiving the packet. By using the stack snapshot, we are able to solve the stack consistency problem and allows the stack and NF processing to be performed asynchronously. For NFs without dependencies, we can do forward optimization and achieve the full parallelism of stack and NF processing. Parallelism isn't our main focus, so our current implementation only focuses for read-only NFs. But ideas from other work, such as NFP and Parabox, could be added to macroboxes to improve this. Finally, to maximize performance in a multi-core environment, we can run multiple copies of the same stack on several cores, and ensure all packets from a single flow will be sent to the same stacks and NFs to keep flow consistency. Okay, so far we are still using packet interface to describe the consistency problem. But ideally, we want a more flexible and general interface, since NFs operating at application level care about data instead of individual packets. Then we came up micro event, since an event can encapsulate the data and notify the subscribers. A stack could produce a set of packet level and flow level events, and each NF may be interested in some of them. For example, NF1 wants to be notified when a TCP SYN packet arrives, while NF2 wants to get batch stream data. At the same time, an NF could also generate its own events, such as NF3 could publish an event when a flow is identified as malicious. Based on these categories, we organize events as a hierarchy. The root is the simplest type event, and then packet-based events which are triggered for each packet, such as packet/TCP. And flow-based events which represent state changes for the entire flow, such as flow/TCP. Both packet events and flow events are generated by the macrostacks, and we use X/Y to represent the event extension, where a new sub-event can be created by adding extra fields in addition to parent fields. For example, packet/TCP can be further extended to represent TCP FIN event. Another category is NF events, which are generated by the NFs instead of macrostacks, and can also be incorporated into this hierarchy. For example, an IDS might define an event that signals a packet matches a malicious signature. Our current implementation has focused on TCP, but developers could also create their own macrostacks for protocols such as QUIC or UDP, and define events for those in the hierarchy. This event hierarchy serves two purposes. First, it provides abstraction of data structures to simplify type checking, and offers a more flexible way for NFs to filter types of events they want to receive. Second, it standardizes the pub/sub system setup, where NFs subscribe to portion of the hierarchy and also gets the sub-events. For example, NF could subscribe to packet events and receive all types of packets, or only subscribe TCP packet events to ignore packets from other protocols. Next, let's see how pub/sub works. Each NF announces its input ports, which are publications, and output ports, which are subscriptions, with the event type for each port to the macrobox's controller. The controller stitches a group of NFs together by linking input and output ports of NFs, and performs type checking using event hierarchy to ensure NFs will be able to interpret incoming event messages. Then the controller translates the pub/sub into a flow table with service chain rules to allow fast event propagation. So when an event is triggered, the NF looks up the flow table for the next hop without doing full pub/sub lookup. And we can see the pub/sub architecture could provide convenient higher-level interfaces based on the flow of events rather than the flow of packets. Now the implementation. Macroboxes can be viewed as 5 layers. At the lowest layer, we use DBDK to send and receive packets over the NIC. On top of DBDK, we use OpenNetVM to set up NF communication and manage individual NFs as well as chains. Then we implement microstacks based on MOS and MTCP with significant changes to support stack sharing and customization. And we use macro-event pub/sub interface to replace previous packet-centric model. Finally, we ported a set of applications using our event and stack APIs. In the evaluation, we are aiming to answer 2 questions. Does macroboxes improve the performance by removing redundancy? Can macroboxes provide customized stacks based on application requirements? Our evaluation was performed on the NSF Cloud Lab. To To evaluate the benefits of removing redundancy, we first put MOS into our NFV framework. Since a straightforward part of chain MOS NF is using a packet interface between instances and performs stack processing for each NF. In contrast, our macroboxes only need to perform stack processing once, and then forward the stack events through the chain of NFs. For both cases, NFs themselves perform negligible processing, and we use a workload of 4,000 concurrent web clients accessing 8 KB file. From the results, we can see, as the chain length increases, the throughput of macroboxes remain almost flat, while MOS drops quickly. We do see a decrease for both cases when the chain is longer than 6, since they have to use cores on another socket and pay NUMA penalties. Batching events and each NF could further improve the throughput of macroboxes, and we use batching for the remaining evaluations. And this experiment shows that removing redundancy is important and can improve throughput by a factor of 2 or more. Next experiment, we show how our microstack modules can provide different performance and functional requirements to meet the NF's needs. We use NGX as web server and AB as client to generate traffic. And we compare against the baseline of the simple L2 forward and HA proxy, a popular open source load balancer, which uses Linux kernel-based stack. Here, we only show the latency result, and please refer our paper for other details. The first load balancer solution using macroboxes is the L4 load balancer, which is based on our layer 2 and 3 macrostack and can get a latency close to the forward case, as it only looks at the header information and does minimal TCP processing. This load balancer can be used for simple scenarios where redirection does not need to be based on application data. Next is the L7 load balancer, which is based on the Spicer macrostack, and it adds more overhead, but also more power, since it can redirect the connection after looking at the application data to select the server. Next, we consider a solution where we combine our L7 load balancer with the light HTTP server running on the endpoint macrostack. And we consider the case where 50% of the requests are redirected to the local light HTTP server that acts as a fast cache co-located with the load balancer middlebox. This solution could beat the L2 forward case because the local cache web server is integrated with high-performance I/O framework. Finally, we redirect all requests to the local cache, and this achieves the lowest latency among all of the solutions. These results show the power and flexibility of macroboxes when combining NFs and endpoints onto a unified platform. We believe this could change how developers think about building applications, since we are blurring the line between middle boxes and endpoints. If you are interested in working on network functions with TCP endpoints, we have already released an update to our OpenNetVM platform in collaboration with the MTCP developers. And you are welcome to our HPNFV tutorial on Friday to learn more details. Okay, to conclude, we are targeting 3 issues of current NFV frameworks: redundant stack processing, a monolithic stack, and separate stacks and interfaces for middle boxes and endpoints. And we designed and implemented Microbox based on 3 corresponding ideas: consolidated stack processing, customizable stack modules, and unified event interface. In particular, Microboxes include 2 main parts, macrostack and macroevent, and uses techniques such as stack snapshot, parallel processing, event hierarchy, pub sub interface to achieve efficiency and flexibility. With this, I'd like to end my talk, and I'm ready for questions. Thanks.
Everton Cordeiro from UFRGS Brazil. Have you given thoughts on how to provide support for fault tolerance in your middle boxes, in your network functions running your architecture? And second question, how could you work with scaling up and scaling down of network functions, and especially to migrate network functions in between endpoints in your data center using your architecture?
Okay, good question. So let's start with the fault tolerance one. So actually, when we start with the project, we choose a pipeline model where we assume our apps are running on isolated containers or virtual machines, compared to another model, which is a monolithic model, like NFs and stacks are combined into a monolithic process. And in this way, I think we could easily achieve fault tolerance better than the other model. This is one of the design of our model. Mm-hmm. But in this paper, we haven't done any fault tolerance extensions, but that might be a good direction.
Okay. Mm-hmm.
And the second question is scaling. So also for scaling, so if you look at our implementation, we are based on the OpenNVM platform. Mm-hmm. And actually in our platform, we could support automatic scaling in a single machine by using our NF manager to monitor the status of the NFs and do the auto scaling. But as far as for the multi-host scaling, we haven't done that part. Mm-hmm. But this could be a future work.
And for migrations, migration of network function, migrate the context of a network function from npop to another one, the data center. You also have support for that, or could naturally accommodate that in your architecture?
I think one of the challenges for migration is how to, especially in the NFV world, is how to maintain your state.
Yes.
Yes, mm-hmm. Since in our, we try to decouple the stack from the NFs, this actually could simplify that problem. Mm-hmm. Because all the states are kept in the macro stack. Instead of using traditional model, the stack are kept with the NFs.
Mm-hmm. All right, thank you.
Thank you.
Hello, Luis Pedrosa from EPFL. Interesting work. I have a question about how you achieve isolation. You mentioned that you have VMs, but what technique do you use for that? Are you using an actual hypervisor? Are you using some kind of jails or containers or para-virtualization or some other mechanism altogether?
Yes, so in this work, we just use the containers. But in our previous work for NetVM, we start with the KVM with virtual machines.
And
based on the hypervisor KVM.
And is there any overheads due to the sharing of information? Because you have to pass information across these NFs. Is there any overhead due to that?
Yes, so if you refer our NSDI paper, we try to provide a virtual machine-based platform and avoid those overheads on the KVM. But also in the recent works, for example, the NetBreaks, they also try to achieve the fault tolerance using the Rust language.
In that case, they don't have any virtualization. That's the point of that work, exactly.
Yes, I'm just mentioning different ways to achieve the isolation. But in our ways, we try to separate the stack and NF into different containers.
Thank you very much.
Thank you.
Our next speaker is Ratul from UPB. Right now he's a PhD student there. He's besides a good presenter, he is also a very good cyclist. He actually rode a bike for 4 days from Romania to here to give the talk. So let's hope to have a very exciting talk.
Thank you. Going back to verifying P4 programs, this is debugging P4 programs with Vera. Since debugging is a very broad term, I'll begin by framing our work a bit more precisely. We do static verification of functional correctness for P4 programs. Static verification because we don't generate concrete traffic, we don't deploy real devices. Functional correctness, we check for the obvious programming errors in P4, such as invalid memory access, parsing deparser errors, but as well, we do checks for higher level properties such as correct policy implementation and so on. We do this assuming correct functioning of the P4 infrastructure, such as the compiler and the device itself. I'll skip the customary P4 introduction and I'll dig right into it. This is a P4 program. It doesn't look like one, but trust me, it is a P4 program. This does IPv4 routing and then IPv4 encapsulation. You know this because I've told you. However, if you wanted to come up with this information by yourselves, you had to look at the deparser specification. This dictates what input and output the switch accepts and produces. Next, you had to look at the match action table declarations. These dictate the possible actions the switch can take on packets. And lastly, the control program will define the sequence of match action tables that are going to be applied for each packet that comes in. In our case, this is the parser. It declares two headers, the Ethernet and IPv4, and parses them accordingly. Now you're already P4 savvy, and you might recognize a problem here. I've told you we should do P4, we should do IPv4 encapsulation. However, our parser, which is also used by the deparser mechanism, only specifies one IPv4 header. So we won't be able to encapsulate IP in IP packets. Okay, let's fix this. We added another header declaration, the IP in IP header, and we'll move on to have a look at the control program. This is extremely simple. We only check for the validity of the TTL field, and when we forward the packet for longest prefix matching and routing. What can go wrong, right? Well, going back to the parser, we can observe here that our switch also accepts non-IPv4 packets, in which case the TTL value will have an undefined value. So the correct thing to do here would be to add a validity check before we compare the TTL field. This is how it would look like. However, this does not mitigate the problem completely because we're still accepting non-IPv4 headers, in which case these will fail the validity check and then they will get forwarded to the buffering mechanism with no egress specification being set, in which case the behavior is undefined, target dependent. Fine, okay. Let's move to a table declaration. In this case, the in-cap table. Maybe we're more lucky. Again, the behavior is very simple. We add another IPv4 header. We set the header fields to correct values as specified. Again, this looks very good. However, we modified the parser. Now our parser can also accept encapsulated packets. And in this case, trying to add another encapsulated header will again lead to undefined behavior. We're basically either modifying the existing header or depending on the implementation, we're just going to mingle both. So these are the problems Vera is tackling. Besides these obvious goals, we were driven by three other objectives. We wanted it to be as easy to use as possible, to require little to no intervention from the developer. Whenever this is not the case, when you would like to specify more complex properties, we didn't want to sacrifice generality, so we can optionally take as input a policy specification. And lastly, to be useful in real-world scenarios, this had to be scalable. We went to work we applied Vera to the more common P4 programs that we could see here. These are on the left-hand side column. And I won't spend too much time on this table. There are two takeaways. All these programs exhibited one of the problems Vera can detect, at least one of the problems we can detect. And verification takes in sub-second time in most cases, and usually under a minute in the worst. This is what Vera achieves. Let's see how it works. Everything starts with a P4 program and concrete P4 table entries. These are then fed to a P4 to Cephal compiler. Cephal is a modeling language. It is custom developed for fast symbolic execution. This is then fed to our custom-built symbolic executor called Symnet. This was slightly modified to perform these bug checks as it runs, and also to allow for a policy specification if this is the case. This is an optional step. When execution finishes, the result is the set of all possible paths through the P4 program, the header values, the constraints, a full instruction trace for every path, and if that's the case, the bug type that Vera discovered. Okay, going back to our running example, let's look at this process in more detail. This is the P4 program. It all starts with the parser. We use the parser to generate all the possible header layouts. These correspond to all the possible paths through the parser graph. We simply walk the graph. In this case, we have 3 possible layouts. Let's pick one of those. Vera is not that lazy. It will pick all of them and continue execution. The depiction, the symbolic depiction of this header layout is this. All the header values have symbolic values, the stars, except from the Ethernet type, which is now constrained to a constant because it went through the parser, and this is the result. This is then fed to the control program. Beforehand, we have to compile this to a Cephal model. The corresponding Cephal model looks like this. This is a labeled instruction block called ingress. As the symbolic packet arrives, because the TTL field is symbolic, we branch execution. These 2 paths will continue independently. On one, the TTL value is greater than 0, and it will then be forwarded to another instruction block called table longest prefix match. Independently, as I said, the other path will continue execution and will be forwarded to the buffering. I'll now take a step back and take you through this process across an entire P4 pipeline. Again, it starts with the parser. We land this, we get to this header layout, Ethernet and IPv4. After the ingress processing, we get 2 paths. One is forwarded to the routing table. In this case, we accumulate a greater than 0 constraint on the TTL field. We move on. Once we do routing, the IP destination field will be constrained accordingly. We perform encapsulation. We add another header. We set the values accordingly. And now this packet is ready to be forwarded outside of the switch. Now, let's go back to the other symbolic path, that corresponding to non-IPv4 packets or those having a less than 0 TTL value. As I said, these will be forwarded to the buffering, and since they have no egress spec set, an error will be reported as they are stuck mid-pipeline. It took us about 5 minutes. Vera does this in about half a second for all the possible header layouts. And for the sake of completeness, these are all the possible symbolic paths through this pipeline. And we can see there the green one exits successfully and implements the switch logic. the other ones fail due to some various problematic conditions. Okay, now I'll switch gears a bit and dig into the nitty-gritty details of Vera. There are 3 things to look at. First of all, scalable modeling of match action tables. Symbolic table entries, this is the case where concrete table entries are not available or we don't have a controller to test our P4 program against. And lastly, the implementation of the policy language. I only have time for one. Please look at the paper for the rest. I promise they're pretty interesting. So, going back to the running example, this is a table. It does a very simple thing, longest prefix matching and then forwarding. These are some concrete table entries. So, the easiest approach to tackle this problem of modeling this table would look like this. This is a sequence of cascading if-else statements. And the problem is, if we look at what it takes for the symbolic executor to reach this path, and making a short digression, the symbolic executor will explore all the four possible paths, but let's look at the last one. First of all, it will accumulate the obvious condition that the destination should belong to 0/0, but also all the other previous conditions negated. And these will be sent to our constraint solver, Z3 in our case, to be verified for correctness, to test their satisfiability. And looking at this, we can easily see that some of them are redundant. In this case, one that is more general will render the last one redundant. So think about this algorithm implemented across a table. We'll end up with n squared constraints, most of which are redundant. In our case here, 3 out of 10 constraints are redundant, being implicit from the others. So at the other end of the spectrum, we would like our code to look something like that. Fork execution on 4 distinct paths and only add the direct constraints here. This is super efficient. However, it has a small problem, is incorrect. Because if you look at the 4th path, the one belonging to the default route, this will be taken by any packet. So we need to make sure this strategy is correct. So we need to add some more constraints to make this correct. But we don't want to add the n squared number of constraints. So we need to find the optimal number of constraints, and we would like to do it quick enough. With this goal in mind, we devised a tree-like data structure that would help us compute this optimal number of constraints. In this data structure, the more specific constraints sit at the bottom. Then towards the root, we add the more general ones. Every link in the tree depicts an overlapping constraint, one that we have to do something with to make it correct. Now, for generating constraints for a given node, we obviously have to add the direct constraint, and we only need to look at the direct children of this node. In this case, 1 children. And this process will become more clear if we look at the default route. Here, we only have to look at 2 neighbors, and this will render the minimal set of constraints that need to be added to mitigate overlaps. So, in summary, we using this data structure, we can compute the optimal number of constraints required. This is fast because we only have to look at the neighbors of every node. And lastly, it works for other matching strategies such as range matching and also tables with multiple matching fields. We build a multi-forest of these trees. We implemented this and tested against some other model generation techniques. And I won't spend a lot of time on this table. I just want to show you two things. First of all, the naive approach quickly runs out of time. It takes 1 hour for rather small tables. Now, comparing the Vera data structure against our previous in-place heuristic algorithm for determining this minimal number of constraints, we see that we achieve basically the same runtime, being optimal in size. However, with a small trade-off in space, we gain a lot of time in terms of model compilation. This was Vera. There's other work out there, as you've already seen. Our closest neighbor is P4V. They take another route towards solving the same problem. They make heavy use of assertions, which is a good thing. We think it might help. It might help reducing the runtime of verification. However, this brings a burden on the programmer. Packet for P4 packet gen takes a different approach. They generate concrete packets to test metal implementations of the P4 behavioral model. And last but not least, we compared to P4 node. They try to solve a more high-level problem. They examine whole networks consisting of P4 devices, and as a result, the class of bugs they target is different. So with this, I conclude my talk. Most P4 programs contain bugs. We think this is because P4 is very close to the hardware. Vera automatically finds these bugs with no developer intervention in seconds. And we can deal with the case in which there is no controller or no concrete table entries to build a model. We use symbolic table entries. These create a super approximation of the behavior of the P4 switch. This can introduce false positives, but this is all we can do in the absence of a P4 controller. We're also planning on releasing Vera open source. We're cleaning up the code, and with this I conclude my talk, and I'm happy to take any questions and suggestions.
Hello. Hi, Ratul. This is Ratul from Alibaba. Nice work. My question is, you compare with P4V, saying that they need some assertions to describe behavior, but you don't need. But I was wondering, without assertion, how are you going to describe entire behavior of a P4 program? For example, for some large P4 program like switch.p4, it's actually a realistic switch, right? So how are you going to describe the whole behavior of that for your verification?
Yes, in terms of, we can catch without any developer intervention these obvious problems such as memory access, invalid parsing, and so on. For logic problems, we need to rely on a policy specification, of course, yeah, because, for instance, I can give you an example. Who tells me which valid values a field can take? So we cannot do this without intervention.
So you also need to define the properties of this P4 program and validate whether the property is valid.
Yeah, for high-level properties, we use NetCTL specification language.
Okay.
Yeah.
That also defined by human being.
Yes, yes.
Thanks.
Thank you.
Hi, Radu. Very nice talk. I liked it as much as the P4V. As a matter of fact, Arseniy Zasranik, IPFL again. I wonder how do you deal with packet recirculation? Do you have some special mechanism? Does it pose additional challenges?
Alongside these, going back to the table, I'll try to do this very quickly and see if we can do this. We also perform loop detection implicitly in the symbolic executor. So, okay, so the second to last column in the right, we can perform loop detection, in which case we detect packets that would flow indefinitely through the pipeline. This is the answer to your question?
No, I meant the different aspect of it, like when a packet gets recirculated, do you consider it as a fresh packet with all the state how it anew, or do you extend your pipeline effectively multiple times?
I think there are multiple instructions to perform this recirculation, clone, and so the simple action, the simple answer would be that we allow calling a previously executed cephal block. So virtually we can re-execute the whole pipeline as many times as necessary. With the values of the header dictated by the instruction that created the recirculation.
And how do you prevent looping in this case?
How do you, sorry?
How do you prevent infinite loops in this case?
We have a loop detection algorithm. Fundamentally it works because the packets have a limited amount of state. So we basically check for state duplication as we perform symbolic execution. Whenever we see the same packet, we report it as a loop.
Thank you.
Thanks.
Hi, this is Praveen from Princeton. Did you consider the cases where the packet path changes because of change in the traffic conditions in the data plane?
You're referring to registers, meters, things like this?
Yeah, some queue length, meters, something like
that. Again, I have a short answer and a long answer. The short answer is we don't deal with state that is shared across paths. However, for instance, if the path condition depends on a counter or a meter, we can give you the result saying that on this condition, if the counter is equal to this value, this packet will take a different route. So we can model that like this. We don't know if that variable will ever get to that value, but we can report this in the output.
Okay, thank you.
Thanks.
Okay, let's thank the speaker. Okay, this is the end of the session. We're going to have a break.
Yes, is Margaret Chiosi from FutureWay here? Yes, we have a phone for you. And the rest of the people, volunteers, should be collecting the forms at the door, but you also can drop it off at the registration desk and also give it to me or anybody from organizing committee.